Okay, our presentation is made together with one of the Latvian company working in space sector, in Eventech, which is specialist in the event timing technology. First, a few words about laser ranging, just for introduction. This is a very old and classical picture from Geoscience of Australia, which illustrates the main principle of satellite laser ranging. It basically goes down to measure very precisely time intervals for the laser pulses traveling to the satellite and back. In turn, we get a very precise ranges, and they have quite a lot of the important applications in space geodesy, time transfer, precise orbit determination, and also some new applications like a space situation awareness. And here goes, before we are going further, the measurement principle relies that we have the single photon detector basically, and we have to measure the time, or to more precisely, timestamp the events with accuracy which goes down to few picoseconds to reach accuracy, which we're talking about, have some sub-centimeter accuracy. So basically, we are measuring distance to satellites with accuracy about, regardless of the distance, is either 500 kilometers or 20,000 kilometers, or maybe up to the moon with a sub-centimeter accuracy. So before we going forward, few terms we are using. These are also used in the air defenses and radars. The first thing is such a term as a range gauge generator, because to get the signal, we usually have the we have to usual approach is just to we know approximately when we expect the signal and we gauge the detector. Here's the catch, because the another thing is each detector, or most of them, have so-called dead time. Basically, this is time period after registering the photon or incoming photons. The detector is blind for some time. It can be very short, but it can go up to 1 microsecond. And if we convert it to the time domain, it's quite a lot. And so we have to guess or try to find this proper range, and before setting up this interval, when to register the event. Another aspect, otherwise we get swamped with data about a bit later. And here comes our problem. We are starting to go into the range objects with very, let's say, not well-known trajectories. And independently, me and the Eventech colleague come to some kind of this, what we call the full record mode. Basically, the idea I mentioned, we are gating the detector or timer, and it's, let's say, the system works in sync. We are triggering the laser, we are measuring the start, we are setting the time interval when we expect the return, and register the incoming event. But here there's a chance to lose the signal. It also happens with the radars. Sometimes you are just not guessing how the plane is flying, and the target is lost, and you have to search for it again. Here, there's a similar situation. And the one idea is to somehow realize this search mode, also in laser ranging, and get this requires a target. And this requires, so we have the, say, free running detector. Basically, it's a photon detector, which has very small or virtually zero dead time. And also the rest of the hardware also has to be with this small dead time as possible, because when we have these dead times, the system is blind to the incoming signals. So, and here goes the rationale. We had an ESA project about implement the so-called bistatic or multistatic laser ranging. The idea was, it was realized first about 10 years ago in laser ranging, that if we illuminate the target with a high intensity laser, we can get and register scattered photons not only from the transmitting station, but also from receiving. Some other stations, we are just passive, we're just listening or waiting for incoming photons. And here comes a problem. First thing, we need to synchronize clocks very precisely in all stations. It can be done. This is not, let's say, a very tricky issue, unless we are going for very high synchronization accuracies, going down to below 150 nanoseconds or less. And second is, if you are using the range gate generator, here comes a problem. If we are setting the gate, we have to know first when the transmitting laser is firing. This is the first part. And second part is we have to, again, guess the gate. In this case, we have two uncertainties because the atmospheric conditions is slightly different in each station. We have to know when the station is transmitting the laser pulses, and gating becomes tricky. And also, here comes another player, the laser repetition rate, which can be starting from 10 Hertz and go up to the hundreds of kilohertz. So, and here, this is why we come to this idea, why to try to replicate all this gating stuff on the receiving station, just use this so-called full record mode and just record everything. What we need for it? We just need the free running detector, and we need the event timer, which can sustain the high event rates. So, and we already had the detectors. It's basically a type of PMDs. It's called hybrid photo detector. It's a kind of semi-forgotten device. It's still used, but it's not much publications on it. It was quite a noise on the 10, 15 years ago, but now they are, you can buy them, they are used, but there is very little papers on it. And second thing is there was event time, and here we were lucky because Eventech developed a new device, which is called the Event Stream Time Tagger, which can record and sustain up to 25 million events per second. So it's not kind of buffer. You can use this for, let's say, for 1 second, few seconds or minutes. You can just run it for 10 minutes. And it can record up to the 25 million events per second and tag these events with accuracy about 1.5 picosecond. And the second, it has dead time, but it is, let's say, acceptable. It's only 40 nanoseconds dead time. So basically, our system operates with a 40 nanosecond dead time. And then comes the next. So we have the setup. It was very lucky for us because we really struggled with the settings, these gates, and we're trying to use, we also have some quite primitive range gate generator. We borrowed one from the Potsdam, but this system becomes messy very quickly. And so first we tested it with our own system, just to verify the concept. So we shoot our own laser, but we are kind of recorded everything which comes down. And here is an example with satellite. And what we did, we just recorded everything which was during the session, and then post-process it. It's kind of similar in the radio astronomy when you correlate to data sets. Here we have the one separate data set with the laser firing times, and second, which comes from the event timer, which has a time tag the incoming photons. And then we're trying to process, and here you can see very clearly effect of what happens if you set the gate not correctly. Here is let's say we first process it with a software range gate, because we can play, we have the full set, we can set the gate with whatever we want, and just look what falls inside. This is some 50 kilometers in both sides of track. Here is quite a lot of noise, but not much. Here we narrow the gate, so it's only a few kilometers around the real track. And if we set the gate wrongly, you can see this x-axis, which just represents seconds from the last step, we can cut off of the last segment. And this can happen also in real tracking when you set the gate wrong, incorrectly, or just miscalculate or misestimate the distance satellite, you may lose signal. In this case, in this full record mode, you can recover it, just set the gate wider and reprocess it. But if you are doing it in the real time, then the data is lost. You are not getting returns, which is quite common scenario when we are tracking, say, object with a not so well known orbit. So, and here is the experiment setup. We did last year this multi-static ranging with the Borovets and the Grass Observatory, which both has a high intensity lasers. The characteristics are Borovets laser is only 10 Hertz, but here is a catch. Borovets laser has some kind quite large uncertainty of the laser trigger time. Despite that they are triggering the laser according to the UTC timescale, the actual trigger time with the laser it was fluctuating. And if you don't have the laser fire times, it's simply impossible to process the data because we don't see anything, just noise. And grass laser, which has a higher power, so this was quite a small power laser. It was 250 millijoules in green. Grass laser is 200 Hertz repetition rate, and I think it has about 40 something like millijoules per pulse. And the distance is between the, and we successfully managed to get this biostatic experiment in full record mode, the data from both stations. Here, one illustration is from the graphs. So on the upper left, again, this plot. When we see this is on x-axis, again, this is seconds from the past start. And here is a gate setting. This, in this case, not the gate, but we have this predicted two-way range. So because in this case, we are calculating range from the transmitting station up to the satellite, and then downlink to the down pass to the satellite to the hour. And we have to take in account, of course, Earth's rotation, that while the laser pulse is traveling, everything is a bit moving during this small period. And this is observed minus what we observe minus what we estimate. And we get such a curve which we can later to fit and to get already try to improve the orbit. And the interesting thing on the upper right is our all-sky camera, which shows the sky, how it looked like during the experiment. Important part, the sun was just -7. It's just end of the civil twilight. So basically, it's just when it becomes dark. Usually for space debris, it's norm is -9 below horizon to start everything. But we manage also to do when we just basically in the twilight almost. And here how the satellite path looks in grass. So this is quite a straight hours ahead. The total duration is about 5 minutes. And this is how it looks on our side. We have in this low in the South Sea. So basically it's by just below between 20 and 30 degrees of elevation. So it's quite low, and astronomers know that there is quite a lot of air mass in this region. So it's that we get these returns, it's quite impressive. And on this all-sky cams, it looks like about this region. And also it illustrates that the graph we get here, when the grass track was ended, we just start to get the returns. And you can quite see an acquire satellite finally was in sufficient elevation to get something. And then it vanishes because grass is already going down and they are stopping to track at all. And the object was some kind of a rocket body with a radar cross-section about 7.6 square meters. So, some conclusions on it. So first thing is full record mode is not a full replacement for range gate generators. It's just another tool that has some prerequisites to operate. It certainly has applications. It's a space debris tracking, or also in CubeSats, whatever an object doesn't have very precise orbit, and we using the usual approach is setting the gate, we are risking to just not get anything as we see in the before. It may allow also simultaneous calibration together with a laser ranging. It's a bit specific issue, but maybe. It may have some LiDAR application because if there is some cirrus clouds in the laser path, we may get returns also from them. It's just a side effect. It's not, maybe there is some application, maybe not. And the next step, we are looking how to implement this full record mode in real time, because what I will talk about before, it's just post-processing. But to get this filter, this huge amount of data in real time is a bit challenging. Just for illustration, the path which I show has about 68,000 laser start tags and 33 million of the stop tags, which we have to sort and match and identify where this track is. And that takes quite a lot of time. I just run this very naive Python type script. It goes for 40 minutes about, but it is without any optimization, just let's say brute, just write as it is. So our next attempt will be try to get what we can do, which kind of hardware assistance and software improvements we can do to implement this full record mode, also in monostatic mode, and just to enable this real-time feedback. Because important, if we don't see the satellites, our only idea, if we are hitting it, is just to get this return information. Otherwise, it's doesn't make much sense. Okay, that's all for it. Thank you for your attention. And